Hello, Professor. This is Naga Venkata Bhavana, Vinnakota. I'm explaining about my project. My project name is Understanding the Impact of Cache Locations on Storage Performance and Energy Consumption of Virtualization System. In this topic, I'll explain about some of the main topics which is used in this research paper. Sorry. This is the first one, virtualization and storage challenge. In this, we have three topics of increased server consolidation, high application density, and traditional storage struggles. In this first one, we are explaining about the increased server consolidation. In this, we have subtopics of resource utilization, high application density, traditional storage struggles, and the sorry high application. First one, we will discuss about the increased server constellation, and this virtualization allows for a high degree of server consolidation by enabling multiple virtual machines to run on a single physical server. This improves resource utilization and reduces hardware costs. And consolidation leads to improved scalability as more or VM can be added to existing service rather than provisioning new hardware. Second one is about high application density, completing for more storage resources. In this, with multiple VM hosting services on a single physical server, these applications share the same storage resources. This can result in contention for IO bandwidth, affecting performance, and the density of applications can complicate it, data management and backup strategies, as the storage system must handle a diverse range of data types and workloads. And the last one is traditional storage struggles. And these are traditional storage systems which were designed for less utilization environments may struggle to keep up with the high volume of IO operations generated by multiple VMs. This can lead to performance bottlenecks such as slow response times and reduced throughput. Traditional storage solutions often face limitations in scaling to meet the demands of a high density utilization environment. As more VMs are added, the storage system may become a peak performance bottleneck. And in this slide, we are explaining about the cache to the rescue, boosting storage performance. The first one is about the frequently accessed data. Second one is faster retrieval. Third one is improved storage performance and responsiveness. Now we'll talk about the frequently accessed data. In this, cache stores copies of frequently accessed data closer to the CPU or memory. This proximity minimizes the distance and timer required for data retrieval, which is crucial for performance, especially in high density utilization environments. Next, we'll talk about the faster retrieval. In this, caches are designed to be more faster than main storage systems. This speed advantages is due to the use of high-speed memory technologies like DRAM or SSDs in the cache layer, compared to the often slower mechanical or even some solid-state drives in the main storage. With cached data, the system can quickly retrieve information without the need to query to the main storage, leading to faster response times and improved application performance. Next, we will talk about the improved storage performance and resilience. In this, by serving frequently accessed data from the cache, the load on the main storage system is significantly reduced. This reduction in loads help prevent performance bottlenecks and ensures that the main system storage system can handle other requests more efficiently. For virtualized environments where multiple VMs may be accessing the same data for similar data, Concurrently, caching can dramatically improve overall VM performance. Each VM benefits from reduced data access times and lower latency, leading to a more responsive systems. Here we have different types of caches. Uh, I'll just simply modify, just briefly tell about the types of the caches. First one is hardware cache. It involves dedicated hardware components like SSD and DRAM. Next one is software caching. Utilizes software-based solutions to manage cache policies and data placement. Next one is in-memory cache. Stores data in the system as RAM to provide ultra-fast access times. Another one is read and write caches, where it is used for stores or copies of data that are frequently read but not necessarily frequently write. And write caches temporarily holds data that is being written to storage, allowing for faster write operations and potentially improving write performance. Next, next type is adaptive cache. Another one is cache size and cache management, and last one is performance monitoring. In this slide, we will talk about the hypervisor side caching, a common approach. In this, we have three types: location, a centralized management, virtual IO, subpath impact. First, we will see about the location and implementation. In this one, hypervisor side caching is implemented below the VM disk file systems, but above the underlying physical storage layer. This means that the hypervisor has a direct control over the caching mechanism, which is a position between the VM as virtual disk and the physical storage system. Next one is centralized management. In the centralized management is one of the key advantages of this hypervisor slide caching, since the cache is managed by the hypervisor IT teams can configure and administrative the cache policies from a single point of control. This simplifies the management of cache settings and reduces administrative overhead. In this, we have uniform policies. Centralized control allows for the application of uniform caching policies across all VM managed by the hypervisor. This consistency ensures that all VMs benefits from the caching mechanism according to the same rules and configuration. The last one is about the virtual IO subpath impact. And the subpath impact, accessing data through the hypervisor side cache involves the virtual IO subpath. This means that data retrieval and storage operations must pass through the hypervisor as a IO stack, which introduce additional layers of abstraction between the VM and the physical storage. Here we have latency con- considerations and CPU utilizations, and we have some of the benefits of hypervisor side caching. Those benefits are improving performance, simplified administrations, scalability. These are the some of the benefits of the hypervisor side caching. And we have some potential drawbacks like latency from virtual IO, CPU overhead, cache coherence, and we have some best practices for hypervisor side caching, which are monitor and tune. Regularly monitor cache performance from adjust configurations as needed to balance latency, performance, and CPU utilization. Cache sizing ensures the cache is approximately sized to handle the workload and data access patterns of your VMs, and undersized caching may not provide the desired performance benefits. Next, in this slide, we are talking about the performance impact of hypervisory side catching, exploring the trade-offs. In this, we have the subtopics as virtual I/O subpath latency, increased CPU cycles, and the last one is limits throughput I/Os. Firstly, we will say about the virtual I/O subpath latency. In this one, hypervisory side caching introduces an extra layer in the I/O path between the virtual machines and the physical storage. This means that every data request must pass through the hypervisory as I/O stack between reaching the cache and then mm, possibly the main storage. Next one is impact on the performance. The added virtual I/O subpath can increase latency potential, slowing down data retrieval compared to accessing data directly from the physical storage. This is especially notable for applications with strengthened low latency requirements. And we have the balancing act. The trade-off here involves the balancing the latency, introducing sorry. The trade-off here involves balancing the latency introduced by the cache layer against the performance gains, the faster access to frequently used data. For some applications, the latency impact might be acceptable compared to the performance benefits provided by caching. Here, increased CPU cycles. We are talking about the increased CPU cycles. The management of the virtual I/O path and the operations involved in handling data transfers between the cache and the VMs require CPU resources. This includes tasks such as cache management, eviction policies, and maintaining coherence. And the limits throughput. In this one, throughput measured in IOPS, input output operations per second, reflects the storage system's ability to handle IO requests. The virtual IO subpath limitations can restrict the overall throughput of the hypervisory side cache. Potential in this we have the potential bottlenecks for high IO workloads such as those involving large volumes of simultaneously read and write operations, and the limitations of the virtual IO path can create bottlenecks. This may lead to reduced IOPS and impact the performance of applications with the IO demands. Optimizing throughput through mitigate its throughput limitations, it may be necessary to optimize the cache size, fine-tune cache policies, or consider alternative cache solutions that align better with the specific IO patterns and performance requirements. Next, here the reduce IO overhead where possible. Optimize the virtual IO path to reduce overhead and improve efficiency. This might involve configuring the hypervisor or storage system to handle IO operations more effectively. In this throughput, measured in IOPS, refers to the number of IO requests a storage system can handle. The limitations of the virtual IO subpath can restrict the overall throughput of the hypervisory side caching, potentially creating bottleneck for high IO workloads a lot. Next, in this slide, we are talking about the energy consumption of hypervisor side caching, the efficiency challenge. In this, we have two topics of increased CPU leads to higher power draw And the second one is about the additional IO operations for virtual IO subpath. First, we will see about the increased CPU activity leads to higher power draw. In this hypervisor catching requires the hypervisor to manage various caching functions such as handling the virtual IO subpath, managing cache coherence, and transferring data between the cache and the VMs. This increased workload places additional demands on the CPU. We have the higher power consumption. In this, the increased CPU activity results in a higher power draw as CPUs consume more energy when they operate at higher utilization levels. The power consumption is further componented if the higher visuals CPU is running at higher frequency or under more load due to the caching operations. Next, about the additional IO operations for virtual IO subpath. In this, the virtual IO subpath introduced by hypervisory side caching involves additionally IO operations to manage the caching layer. This includes metadata operations, cache lookups, and data transfers between the cache and the main storage. Next, here increased energy use. Each IO operations consumes energy and accumulate at the effect of additional IO operations due to the virtual IO subpath contributes to greater energy consumptions. In this slide, we are talking about the introducing VM side caching, a potential solution. In this, we have cache locations. Next, bypass virtual IO subpath for cache hits. Next, we will see about the potential lower latency and improved energy efficiency. First, we'll see about the cache location. In this, in VM side caching, the cache resides within the virtual machine close to the application that frequently access the data. Next, we will see about the local cache. By By being integrated into the VM, the cache can be optimized by the specific data access pattern and needs of that VM, allowing for more efficient data handling. Next, about the bypass virtual IO subpath for caching hits. In this, one of the key advantage of VM caching is that it bypasses the virtual IO subpath when data is retrieved from the cache instead of routing data request through the hypervisor IO stacks. Next, we will see about the potential lower latency and improved energy efficiency. Because of VM side caching bypass the virtual IO subpath, it can offer lower latency compared to the hypervisor side caching applications. So applications benefit from faster data access, which is particularly advantageous for latency sensitive workloads or reduced CPU overhead. Next one is energy efficiency. Another one is performance improvement, customization, challenges and considerations in this VM side caching is first one is cache management, next is scalability, next is VM specific caching solutions, monitoring and tuning, energy aware design. These are the subtopics of in this VM side caching. Next, in this slide, we are talking about the advantages of VM side caching, exploring the potential benefits, reduced latency for cache hits. As discussed earlier, VM side caching allows VMs to directly access data from their own cache hits without involving the virtual IO subpath. This significantly reduces latency compared to hypervisor side caching, where every access goes through the subpath, including delays. Next one, we will talk about the lower CPU overhead from for cache management. With the VM side caching, the hypervisor is no longer responsible for managing the cache. By this, not having the responsible, this may reduces the CPU overhead associated with managing the virtual IO subpath and data transfers for the cache, potentially freezing up processing power for other tasks. Next, in this slide, we are talking about the potential challenges of VM side caching considering the trade-offs. In this, we have two topics to discuss. First one is about the increased complexity of managing individual VM caches, and next we will talk about the overhead of cache coherence protocols. First, increased complexity of managing individual VM caches, where we are compared to a centralized hypervisor side cache, managing individual VM caches can be more complex, and in the IT administrator would need to consider cache allocation, configuration, and monitoring for each VM. Next, we'll discuss about the overhead of cache coherence protocols. In this, to ensure data consistency across VM that might share the same data, VM side caching requires cache coherence protocol. These protocols introduce additional overhead for managing data updates and invalidation across the VM caches. In this slide, we are discussing about the selecting the right cache location for my needs. First is hypervisor side caching. In this, easier management and suitable for moderate IO workload. Centralized caching simplifies configuration and administration. IO workloads are the good choice for environment with balanced IO demands. Next, VM side caching. In this, lower latency for caching hits direct the access within the VM, reduces data retrieval time. Next, better for IO intensive workloads, improves performance for workloads with frequent cache access. The last one is evaluate workload characteristics and priority, which considers IO intensity, latency requirements, and management complexity. This- Finally, we are about the conclusion of this project. The conclusion of this project is caching plays a crucial role in storing performance for virtualized environments by storing frequently accessed data closer to the processing units VMs. Caching significantly reduces the need to retrieve data from the slower main storage system, leading to faster data access and improved overall performance. Next, here VM side caching offer potential benefits in terms of latency and energy efficiency. By enabling direct access to data within the VM and reducing reliance on the virtual IO support, VM side caching can potentially lower data retrieval latency and improve energy efficiency compared to hypervisor side caching. The choice of cache location depends on workload, sorry, characteristics and priorities. Hypervisor side caching offers similar management and might be suitable for environment with moderate IO demands. VM side caching, while introducing more complexity, can be advantageous for IO intensive workloads where low latency and performance are crucial. This is the final conclusion of my project. Thank you.